Do you see them? Did you see a screen?
Yes, now we see.
Yeah,
Maybe
okay.
it's more beautiful.
Okay. I'm the speaker from the Victor Sacek from the Luz National Technical University, and today our topic is smart greenhouse climate monitoring and control. So our content is problem formulation, methodological-based prototype design and development of electrical frame, software tool development and specification. Discussion, recommendation for future work and conclusion. So motivation and state of the art. This paper is devoted regulating the temperature and humidity of the air and soil, provide optimal parameters of microclimate for plant growth in the greenhouse, developing a microclimate management system, provide optimal conditions for. We developed included a plan for cultivation microgreens with adjustable parameters, climate control system that has been designed with aid of Node-RED visual programming tool for data streams. Selection of effective hardware was optimized. Software solution and experimental studies of growth and development process of microgreens were performed. The proposed system allows measure air and water temperature, air and soil humidity, concentration of CO2 in the air, determine day and night based on illumination, provide heating of the greenhouse, provide ventilation to reduce CO2 and temperature. Irrigation with water at the specified temperature. Objective of the research: development of an effective microclimate management system in protected soil structures is an important task. This ensure the necessary level of temperature, humidity, and lighting for plants through both the year, improve yield and product quality, and reduce energy costs. This work is of great importance for the practical sphere and can have a significant impact on the development of agricultural production. Methodology of base concept development. The development methodology is based on well-known smart greenhouse concept and automated system that allows to adjust microclimate parameters. We adapt this concept figure 2 to use for small private farms in order to derive low cost, the easy to install and operate. We propose to concept and prototype of modern greenhouse are acquired with basic engineering system to support parameters microclimate, water supply, drainage and sewerage, air circulation and ventilation, irrigation and heating. On this page, you can see how schematic of the climate control variables looks. State of space-based control. We minimize energy consumption while ensuring optimal values of microclimate parameters. A dynamic state space system was used to configure the system logic based on experimentally obtained data. The macroclimate control system in the greenhouse regulates and air temperature, air humidity, soil temperature, and soil moisture. That are variable dynamics parameters in the context of state space dynamical system expressed by differential equation. On this page, you can see our prototype that we made in our laboratory. Next, structural diagram based on Raspberry. A block diagram of Raspberry Pi 0V based microclimate control system, which collects data from the DESSERT'2024 air temperature and humidity, DS18B20 temperature, MQ sensor gas level, soil moisture sensor its soil moisture, and controls relays to regulate the fan. LED tapes and water pump. The software part reads and analyzes this data, allowing the Raspberry Pi to automatically regulate the microclimate, ensuring optimal conditions inside the microgreenhouse. Software tool development and specification. The developed software-hardware complex for controlling the climate consists of following main components. Raspberry Pi Zero V is the central element that controls other components, collects data, and processes it. Data collection system model that collects data from sensor DHT22, DS18B20, MQ, and soil moisture sensor. Microclimate control the fan regulates and maintains temperature and ventilation. LED stripes provide additional light for plants. Water pump responsible for watering plants or maintaining an optimal humidity level. Infrared film regulates the thermal regime in the greenhouse. Node-RED, a visual tool for flow programming that allows user to read data from sensors, display them, and control the microclimate through a graphical interface. On this page, we can see how looks our terminal in the Node-RED, our interface. And this is our electrical schematic diagram of connection. The four main external devices used to regulate microclimate parameters are a fan, a water pump, and infrared film with a mechanical regulator and two photostripes. This device uses a large amount of current compared to what microcontroller is capable of receive, so they are connected to relays that the microcontroller can interact with. To monitor the state of the environment, several sensors are used, as I said before, DS18B20, DHT22, and Q135, hydrometer, and we develop method of remote monitoring of greenhouse microclimate parameters. The microclimate of the greenhouse is formed by all systems of engineering equipment, artificial lighting source, carbon dioxide supply, irrigation system, ventilation, and heating. To optimize the growth of plants during their cultivation, it's necessary to ensure the optimal ratio between humidity and temperature in air and soil, carbon dioxide concentration, and light intensity. Humidity and temperature in the greenhouse are measured by the DHT22 sensor. He transmits the received data to the microcontroller in the form of a digital signal to one directional bus. Okay, experimental tests and discussion, simulating settings. With the air humidity regulation chain in the greenhouse, we program the PLC in the CodeSys program. We have the following value of maintained air humidity in the greenhouse. Soil humidity in the greenhouse, it's above from 55 to 18%, plus minus 10. And sensor that measures humidity has an output signal of from 4 to 20 microamperes. This Modicon M172 PLC from Schneider Electric. Series of experiments were conducted on the basis of the scientific laboratory of Woods National Technical University. Okay, Node-RED dashboard includes data visualization, control elements, possibility to interact with them, and templates and advanced settings. On this page, you can see the pictures, how we can see in the Node-RED air temperature, air humidity, and soil temperature. These graphics. Next, we can see modeling of our results. On figure 10, we can see daily temperature dynamic in winter season, where we have two different parameters, like this one, it's smallest greenhouse, and condition number 2 is bigger greenhouse. On figure 11, we can see daily temperature dynamic in spring and autumn season with the same parameters, the same conditions. Here we can see daily temperature dynamic in the summer season, and here daily humidity dynamic. So MATLAB tools. Analyzing the data sets, we obtain result in linear model, which is polynomial of the degree 2 in the following form. As the experiment below, coefficient are calculated with 95% of condition bounds. Using the available MATLAB tools, we calculate the values of daily climatic values. In order for predicting the behavior of climatic parameters, we make the mathematical modeling using MATLAB appropriate to on the figure 14. On the figure 14, the plotting of the data sets is presented. The data frame of daily time is from 0 to 24 hours. We make fit in curve of the loaded data using the appropriate curve fitting toolbox. We use polynomial for interpolation and characterize data using a global fit in order to obtain a simple empirical model. The main advantages of selected polynomial fit is responsible flexibility for data that is not too complicated. On these pages, we can see graphics how, based on the analysis of the obtained results of mathematical modeling of air humidity monitoring, the following was established. The range of reaching a constant value of air humidity depends on the volume of greenhouses, types and pairs of vegetation, and the seasonal cycle of crop cultivation. It varies in the range from 1.5 hour until 2 o'clock at nominal productivity, humidification and ventilation systems. Resulting, we conclude accounting for a significant number of atmospheric parameters, constructive characteristics of greenhouses and physical and biological processes of growing, as well as percents of functional relationship of air humidity with the available level of moisture in the soil and air temperature. Determines the need to design such a system based on experiments and mathematical algorithms of dynamic modeling. Our method of testing the microclimate monitoring was designed based on developed prototype of simple greenhouses, which made it possible to effectively access the physical parameters of the macroclimate. During the experimental tests, it was established that the limit values of measurements of all microclimate parameters meet the current requirements. Medium-term and long-term experimental studies were conducted testing of the prototype of the developed system. The result of test of the implemented system regarding the assessments of the dynamic of the results of observation of microclimate parameters within the daily growing cycle are shown in figures above from 10 to 14, which are able to be used for also for forecasting. Developed mini greenhouse prototype can help reduce the risk of pests and diseases, as they can be effectively fought against and use preventive measures. Proposed prototype is more environmentally efficient because reduce the need to use pesticides and other chemicals. It allows to save water since use small number of water comparatively with traditional agricultural methods, open soil. Because you can adjust the irrigation system for optimal use of resources. As a result, many greenhouses not only contribute to the preservation of environmental resources, but also increase sustainability and autonomy of local agricultural systems. The proposed technology makes it possible to provide the most expedient data transfer between different devices, and it's part of the IoT, Internet of Things, as you know. The developed mini greenhouse solution provides ideal conditions for plant growth thanks to the control of temperature, humidity, lighting, and other parameters. Microclimate. The most suitable conditions for the growth of various species can be achieved. So in our conclusion, in the paper, development of universal and adaptive system of plant growing with automated system was performed microclimate management system, as well as effective microclimate control strategy, providing favorable conditions for microgreens to suit the growing cycle. The analysis was carried out, and the main parameters of microgreenhouse climate regulation were identified. Besides, the laboratory test has been done for the assessments of the main function and meteorological characteristics, and the applied effect of increasing productivity due to use of the developed system. And that's all. Thank you for your attention.
Thank you, Victor. Questions from audience? Do we have any? Be active, please. Yeah, I have small questions because I thought before your presentations that there are a lot of ready-to-use solutions from, for example, Europe or some other regions. Is it right? It's the first question. And what is the advantages of your solution? What is better or simpler or cheaper or something else?
It's cheaper because we can use a smaller amount of the resources. Now,
But
it's cheaper
in
because
any case, you use sensors already. You didn't develop any, as I understand. Right. So you use sensors which already were developed by somebody else. Okay.
so that's cheaper because we can control all the processes that we have. We can see all the results that our sensors give to us with the Node.js system. And also, we, as you can see on our presentation, show few images of our construction that we made on our laboratory, and we made it cheaper as it can be.
Okay, thank you. Any other questions? Okay, there is no questions. So Victor, again, thank you.